96,485 coulombs for every mole of electrons. I'm going to probably, when we go to Faraday's law, I'll use a formula, I'll provide it for you. The simplification, we'll round this off to 96,500 coulombs per mole.
So you're going to provide...
But I'll provide it.
Oh, it's just okay.
I'll provide a Faraday. Okay, so let's solve that problem right now. I'll let you know this, and when the application's going to be clearer, we'll use a simplified version, 96,500 coulombs. It's just going to be more convenient for the purpose of calculation. Okay, but the bottom line is, when you start your work, this is what you'll start with. But as always, rather than memorizing the 300 billion possible equations, you want to know and memorize a few laws. And the laws, when the laws are cast in a mathematical form, that enables you the greatest flexibility. So you take the mathematical expression corresponding to a law and then fashion it into the appropriate form for the problem at hand. That way you're not memorizing a bunch of equations which you'll forget a day after the test or a couple days after the test. You keep reinforcing the law and apply the law, because that's really what we're here to learn, is how to apply the law to a given set of conditions. And so when the question I'm going to ask is, derive the expression for the potential as a function of pH for the hydrogen couple or the oxygen couple. It'll be one or the other. I'm going to be both right now. Okay? This is our starting point. Okay, so having said that, now I'm going to erase all of this and start. And so we're going to fashion this to explain the potential for the hydrogen couple. That's what I'm going to start with. And the reason I'm starting with the hydrogen couple, we're really going to be detailing what happens with water. You have to understand these two in order to understand what's going on with water. And when we electrolyze water, we end up with hydrogen and oxygen, which is produced from the reduction. What's the product of reduction of water? When I reduce water, I get hydrogen. And when I oxidize water, I get oxygen. Okay. But we'll start with, I'll do the hydrogen couple. And the reaction for that we're going to need is so we have to have the reaction. And so this is the half reaction for the hydrogen couple. And we need that for Q, right? So Q, what's Q going to be equal to?
Concentration of hydronium to the -4.
No.
Partial pressure of H2.
Okay, so I take the pressure of H2 squared. I don't need to worry about the water because it's the solvent.
Over H3O.
Over the concentration of hydronium ions, molar concentration of hydronium ions to the fourth power. Okay?
Why is it so cool?
To the fourth power? Still
Oh,
do
it's
that.
okay.
Yeah, here, let me use Mr. Finger. I'm gonna get better with that. Okay, now, so, and what we need to take advantage of is what is the partial pressure of hydrogen when it's produced? What pressure is it produced at? It's produced at 1 atmosphere, and since. So now that I've got Q taken care of, so I just, since this is 1 atmosphere and 1 atmosphere squared is 1, that drops out of the equation and Q takes on this very simplified form. The hydronium ion concentration to the negative. Okay? So now that we have that, we can now plug that into the equation above. And I left out, what is the potential for hydrogen reduction? So we have the voltage is 0 volts. And by the way, you don't need to memorize a lot of voltages, but that one you probably should know. And you might even go with reduction potential for oxygen as well. Anybody know what that one is off the top of their head? 1.23 volts. So that's pretty easy. It's as easy to remember as 1, 2, 3. And so this one's really nothing to remember, and the other one's as easy as 1, 2, 3. So those are 2 voltages that I think you should probably be able to remember very easily. And so now we'll plug it into the equation. And what is Ne in this one? How many moles of electron? 4. Yeah. Okay, so now I have this expression, and the rules with logs allow me to do what? I can pull this -4 through. Okay, so I'll do that. So I pulled the -4 through, and I just sort of rearranged it. I pulled the 4 out front and put the negative sign in front of the log, because this log of the hydronium ion concentration, does that look at all familiar? That's the pH. So we now have it in the form which we need it. And that's going to be equal to 0.0 volts minus 0.05. So now we know under standard conditions, when acid is one of the reagents, what is the pH? What is the concentration of hydronium ions under standard conditions? No? Well, I'm not, okay, asking me, you're telling me the pH? I'm saying, what is the concentration of hydronium ions under standard conditions?
1 molar.
1 molar. All standard conditions require 1 molar for all reagents, right? And so now what's the pH of a 1 molar solution? See, it's a log of 2. log of 1 is 0. And so, under standard conditions, pH is 0 and the voltage is 0 volts. Under non-standard conditions, as the pH changes, it's going to be, the voltage is going to be reduced as the pH increases by 0.0592 volts for every pH unit. Okay, which is why this is a particularly useful form. We'll get to graphing in a little while, but that is the reduction potential for the hydrogen couple. Yes?
Can you repeat that again under non-standard conditions as the pH?
Okay. Let's go, first we got to remember, always go back to elementary definitions. Standard conditions is 1 molar concentration for all solutions, and 1 atmosphere partial pressure for all gaseous products and reactants. And so at that concentration of hydronium ions, 1 molar, the pH of negative log of 1 is 0. So the pH is 0, and so this equation will, this term will drop out, and we get E naught, standard conditions. And now what we're doing, this expression enables us to cover it at all pHs under non-standard conditions, which is where the pH is non-zero. It's going to be greater than 0. That's not really, I guess this would work as well with conditions where it was less than 0. Yeah, you can. So this is the most useful form. So we're going to do the same thing with the reduction potential for oxygen. And I don't want to go over, I'm not going to go all the way back to Gibbs free energy. But you should be able to go from the Gibbs free energy expression for non-standard conditions and come up with this equation. Okay. Did that answer your question?
Yes.
Okay.